We are continuing our lecture series, and today we are looking at Introduction to Linear Programming. So, by way of definition, we can say a linear programming is a mathematical technique for solving linear optimization problems subject to linear constraints. So, in a linear programming problem, one studies the best way to allocate limited resources in order to achieve a maximum objective. Okay, that is if you are looking at it in terms of making profit, we talk of maximization. If you are looking at it in terms of reducing cost, then we look at the minimum cost available. So this particular topic can be applied in various ways. And another example where we can use linear programming is where you have allocation problems, we have transportation problems, distribution problems. So you can use a linear program to actually do all these things using mathematical formulas. So let's say for example, that you are a manufacturer. Of course, you'll be producing several different types of goods. The only problem you will be looking at now is, for example, the labor hours that you have available to you. And the second one could be the machines that you are using. So the labor hours, people are not able to continuously work. Even machines, they break down at some point. So if for the 24 hours, you have a limited number of hours that you can use in performing this task, and the machines too, they get tired at some point. So you will need to look at these as constraints in order to formulate a mathematical problem to solve it and be able to get the optimal solution. So the question now is, how should you allocate the labor and machine time so as to produce enough items to meet the demands in the market? And of course, as you are doing this, you are thinking of also minimizing the cost that you incur in producing all these things. So first, let's look at the properties of a linear program. One, the relationship between variables and constraints must be linear. We're looking at linear, so all the variables must be linear. Linearity, we are looking at the coefficients being linear. So that is the linearity we're talking about here. The model must have an objective function too. So maybe your objective is to maximize profit, or your objective is to minimize the cost. So whichever way it is, you must have an objective function. Third, the model must have structural constraints. So the constraints that you have, you would have to define them mathematically. They should have a relationship, a mathematical relationship. The last but not the least property is that the model must have not negative constraints. If you are going to produce, let's say you're going to cook food, if you don't have the materials for the food, you will not start the cooking. So you can never have negative materials. We don't have negative constraints in this case. This is how a standard LP problem looks like. First, just like the properties we have identified earlier on, you have a maximization function, then subject to some restriction. The restrictions here are what we call the constraints. So the function being maximized here is our C1 x1. So let's see here, that is the function that we are maximizing. So this C1 x1 plus C2 x2 up to Cn xn is what we call the objective function. Now the restrictions normally are referred to as, you've heard me mention constraints already. So the restrictions are what we usually call constraints in a linear programming module. So the first M constraints, that is those with a function of all the variables ai1 x1 up to ain xn on the left hand side, are sometimes called functional constraints. So that's this functional constraints, all these are functional constraints. And then we can have a similar one for the non-negative constraint, and that will say if we can have a similar constraint for the xi's. So you have the xi greater than 0. So every, let's say, x1 should be greater or equal to 0, x2 should be greater or equal to 0, and then xn should be greater or equal to 0. So none of them is going to give us a negative value. That said, let's look at some terminology. You may be used to having the term solution to mean that to mean the final answer to a problem. But the convention in linear programming is quite different. Here, any specification of the values for the decision variables, what are our decision variables? The x1, x2, up to the x that we stated earlier, is called a solution, regardless of whether it is a desirable or not desirable. Okay, so different types of solutions are then identified by using an appropriate objective function. A feasible solution is a solution for which all the constraints are satisfied. That is a feasible solution. We'll use a graph to demonstrate that. So let me just draw that one here. If we have this one as x here and then y here, and we have a line, let's say this is the line. Now the equation of the line probably is, it is not a correct equation. I'm just giving it something. X plus y less or equals to some value, let's say 5. This is the equation that will give us this nice line that we are seeing here. Then we can say that any value that is below that satisfies the graph because we're talking of less than or equals to. So if I pick any point between these inside this triangle and put inside here x1, y1, I'm going to get the value to be either less than or equal to 5. So it means that everyone here is satisfied. Now, this is what we call a feasible solution. All the solution, the points here that satisfies our equation or inequality, we call that the feasible solution. Infeasible solution, on the other hand, is a solution for which at least one constraint is violated. So if this is the case, and unfortunately we happen to have just a single point in the middle that do not satisfy this inequality, then we say that the whole area is not feasible, called infeasible solution. The feasible region comprised of the collections of all feasible solutions. So all the feasible solutions where they are found, we call that the feasible region. So the triangle is called a feasible region. It is possible to have a problem that will not have a feasible solution. Let's look at optimal. What is optimal solution? A feasible solution that has the most favorable value of the objective function is what we call the feasible solution. The most favorable value is the largest value if the objective function is to be maximized, whereas it is the smallest if the objective function is to be minimized. So in this case, this could be the points that will lead us to whether minimum or maximum. So most problems will have just one optimal solution. Our attempt to find the optimal solution, most times we look at the corner points, especially when you are considering the graphical method in solving your equations. So in this case, the points that are already marked the corner constitute the corner points. If we had another graph going through this way, then their intersection will constitute another feasible region, and this would have been out of it wouldn't have been a feasible region. So we would take that off and consider this as part of the corner point feasible solution. Let's take an example so we can see how this is done. Now, the best way that you can actually do this without a struggle is to draw a table and put them inside. Okay, so let's see how we can formulate a mathematical problem from a question. 4 different types of metals, namely iron, copper, zinc, and manganese, are required to produce commodities A, B, and C. To produce 1 unit of A, 40 kg of iron, 30 kg of copper, 7 kg of zinc, and 4 kg of manganese are needed. So let's take all this and then rule here because we will need to come back here for something for these numbers. So similarly, to produce B, we need 70 kg of iron, 14 kg of copper, and then 9 kg of manganese. So that means that zinc is missing, it's not needed here. Then product C, we need 50 kg of iron, 18 copper, and then 8 kilogram of zinc. Manganese is not needed in this one. So the total available quantities of metals are 1,000. This is the limited resources that we spoke earlier on. That is how we are limited to 1,000 kilogram of iron. If you need more than that, you won't get. You can either use the 1,000 or you use less than 1,000, but you cannot use more than 1,000. What you don't have. So 500 kilogram of copper, 200 of zinc and manganese respectively. The profits for producing each of the produce A, B, C are 300, 200, and 100 Ghana cedis respectively. So our problem is to formulate the mathematical model. Now, the ability for you to answer the question or to solve it relies on you being able to identify and write out the model properly and accurately. So if you make a mistake here, your solution is going to be wrong, not because you didn't calculate it well, but because you got the model wrong. So you can have a wrong model and you have a correct solution based on the wrong model, but that won't solve the problem. Our objective is to solve the problem, not to solve something else that is correct. Okay, so the best way that we can have this done is to actually put this in a table. That will make it a less difficult for us to write out our equation. So let me create my table here. Okay, I have three products. So I want to put the products here. See, then I have the materials. I have the iron. I have the copper. I have the zinc, and I have the manganese. Okay. Now I will extend this a little because I want to write it available materials down there after I have finished. So let's look at A first. A, we need 40 kilograms of iron. We need 30 kilograms of the copper. We need 7 kilograms of the zinc and 4 kilograms of the manganese. What profit are we going to get if we do this combination? What profit are we going to get? We are going to get 300 Ghana cedis. Next one, B. B needs 70 kilograms of the iron, 14 kilograms of the copper, and then 9 kilograms of manganese. So we put 9 here. Zinc is not mentioned, so it means zinc is not required in making product B. So I put 0 here. And what profit am I going to get when I finish with this product? I am going to get 200 Ghana cedis. Product C would require the mixing of 550 kilograms of the iron, 18 kilograms of the copper, and 8 kilograms of the zinc. So here, no manganese, I put 0 there, and I get a profit of 100 Ghana cedis. Now, what are the constraints? What is the available iron that we have? We have just 1,000 kilograms of 1,000 here. Okay. Then I have um, copper. Copper is 500 kilograms. Put 500 here. Zinc is 200, and then manganese is 200. So this is the table that describes the whole question that we just read. The next thing is to now write out your equations one after the other. So the first one is to maximize your objective function. Maximize. Let's say we are maximizing profit. Okay, so Z is equals to, you can decide to put any letter but define what the letter stands for. So my Z here is representing the profit. Okay, we want to make profit. So I have maximize Z equals to 300 of A plus 200 of B plus 100 of C. Subject to some constraints. What are the constraints? One is the iron constraint. Iron. So iron, what is how much is iron given to A, iron given to B, and iron given to C. So I have 40A plus 70B plus 50C. This combination should be less or equal to 1000 because we do not have more than that. Next one is copper. Is our copper constraint. We have 30 to A, 10 given to B, plus 18 given to C, and this should be less or equals to 500 kilogram. Zinc constraint, we have 7 of given to A, plus we don't have a B, so that is 0, plus we have 8 given to C, so 80 less or equals to 200. Similarly, manganese constraint is equals to 4 given to A plus 9 given to B plus nothing given to C, so that place is 0, less than or equals to 200. So these are our constraints. Of course, the last but not the least constraint is your non-negativity constraint. So let's look at some algorithms. What are the methods designed for us to use in solving linear programming problems? One is the graphical method. So the graphical method, all you need to do is simply draw a graph using the equation, the constraint equations or inequalities. Then you look for the feasible region, look for the feasible solution, and the optimal one. The one that is going to give you either the maximum profit, the largest value, or the minimum cost, the smallest value, depending on the problem you want to solve. You want a simplex method that is also an algorithm that we have to go through processes until you get to the final stage where you pick out your a combination of your solution. Now you have the northwest corner method, we have the least cost method, and we have the maximum cost method. These are the algorithms that we are going to look at in the course of this series. Okay, so let's look at the first one. What? How do we perform a graphical method? Let's consider an example as this. How do we get this into the graph? You will notice that we have 3 constraints here, or somebody was saying 2 constraints, but sometimes I add the non-negative constraint, sometimes I don't add it in saying the number of constraints. So yeah, look out for that. Whether I mention it or not, you should note that it's part of the constraints. All of that variables should be greater than or equal to 0. So now let's look at how do we solve this problem. Okay. We will need to draw the graph on a graph sheet. Okay, so we have 2 equations. Now we are converting 2x plus 2y plus 5 because we're going to draw the line. But of course, we know the less than will come afterwards. We know which side will be less than, which side will be greater than. Then we shape that appropriately. Then the second one, 2x plus y equals to 4. So let's name this equation 1, this equation 2. I want to solve this simultaneously. And why am I solving this simultaneously? I would want to find out the solution. This is not drawn to graph, so I won't get the correct answer, but I can draw it not to scale and solve the 2 equations simultaneously to get a solution that I can draw and it will be accurate on the graph. Alright, so for now, let's draw the graph as our interest should be. How do we get the line down? Let's get the coordinates. For the first one, for the first equation, let x equals to 0. So if x is equal to 0, our y, 2y is equals to 5. So just divide by 2, divide by 2, and our y is equals to 5 over 2. The next one is if x is equal to 0, we have this. So the first coordinate is 0, 3, sorry, 5. over. Let y on the same equation, let y equal 0, then we have 2x to 5, 5. So divide this by 2, divide this by 2, x equals to 5 over 2. Coordinates will be 5 over 2, 1 to 0. So we have that coordinate already. So 5 divided by 2 would be 2.5. Let's get a second one. On question 2, let's x equals to 0, so that we have y equals to 4. And if and our coordinate there will be 0, 4. Again, on the second equation, that's y equals 0, then 2x equals 4 divided by 2, divide by 2, and our x equals to 2. So our coordinates in that 2 is 0 and 2. So we have 4 coordinates now, 2 per each equation. Let's scale our graph here. Okay, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Again, it's not drawn to scale, so let's see how we can get this done without drawing it to scale. So the first coordinate is 2, 0, 5 divided by 2, and 5 over 2 is 2.5. So we are going to be here. Our 0, 5 divided by 2, and then our 5 divided by 2, the second coordinate, is right in the middle here. Okay. So what we need to do is now draw a straight line. So we draw a straight line that will pass through these 2 points using the ruler. So like this. Okay. And then we can call this one 2x plus 2y equals to 4. The next line, that is the second equation, we have the first coordinate, that's 0, 4. So we have 0, this is where our 4 is, and then 2, this is where 2 is, 0. So again, we are going to rule that line to pass through them. Forgive my lines there. Then name this one 2x plus y equals to 4. Now we have these two graphs perfectly labeled here. Let's go back to the first graph. Let's take 2 points, one here and one here. Okay, so one here would be maybe 2 and then 1, or 2, let me put 1 and 1 that I know is inside. So if I put 1, 1 inside the first graph, which is 1, 2, 1, this equals to 5. No, this is equals to 4, and 4 is less than 5. So that inequality part is satisfied. So it means that I actually have this, I can see here, anything that is below here satisfies that particular constraint, the equation or inequality. The second one is the same way. If I should take the points to the left and the points to the right, the points to the left will satisfy that equation. So I'm going to give one a different color. Okay, so let's redraw this line, and then it's also less than or equals to. So you would realize that there is something here. This I have drawn it to scale. We will have this here being some little triangle there, which will not satisfy the two of them. It will only satisfy this one, it will not satisfy. So we can say that is part of the feasible region. Now the other two constraints that we have at the bottom here, our x and y, they also count, because if you look at what I have drawn, I have gone past here. This is 0, 0. So it means that if y is greater than 0, anything from here going to my right, all these are positive values. All these are positive values, and that satisfies the y constraint. Again, the x2, anything that is here and up, positive. Okay, now the question is, looking at the graphs that I have drawn and the directions of the inequalities, which place will satisfy all 4 equations? of all four inequalities. Remember, this one is standing alone and that is standing alone. And because they are sharing the same right hand side value, we decide to just put them like that. So the four inequalities, they all agree on a particular location, and that is the location we call the feasible region. So let's shade that, and this is the feasible region right here. Okay, so this nice area is our feasible region. Now, what next do we want to do? We want to get the solution, and now our solution will now depend on the different combination xy, the different combinations. If we put that into the objective function, which of them will give us the maximum value? Because here we are maximizing. All right, so let's open and then come here. This right here is our corner point, the intersection between the two lines. Then here is another corner point. We are not taking this because it doesn't satisfy all the conditions, so we cannot include that. Of course, this is another point, this is 0 point, and this is another one. So this one we know it to be 0, 4. This we know it to be 0, 0. This one here we know it to be 0 and 2. What we don't know is this guy here, and that is the one I said we could estimate it if we want to, without actually drawing it to scale. So let's clean here a little and then do our little magic to get it done. Okay, so how do we solve that? We solve it simultaneously. If you look at the two equations that we have, I can use the elimination method. And what is the elimination method? Subtract one equation from the other. Okay, so let's say if I want to subtract 2 from 1, so equation 1 minus equation 2 will mean that 2x minus 2x will be 0. 2y minus 2y will be y equals to 5 divided, 5 minus 4 will give me 1. So already I have one solution. The next one is I choose any of them to solve my problem. So let me go with equation 2. 2x plus y, which is 1, equals to 4. So I'm going to have 2x, which equals to 4, 1. So x equals to 3 divided by 2, 1.5. So our intersection here is actually 1, comma 1. So this is our corner point at the intersection. Let's get this down. We are going to need them, so let me write them clearly at the top here so we can go to the next slide. Use them. 0, 0, 4, 2, 0. Actually, here is 2, is the other way around. Then we have 1 and 1. So these are the four corner points that we are going to look at and see which of them actually will give us a maximum profit. Again, I'm going to take this off to give room for some other calculations. So I'm going to draw a table like this and put our point there, here, and put our z. Z is equals to the objective there, 3x plus 2y. And the first point is 0, second 4, 0, 5. These are the points I'm going to be looking at whilst considering the objective equation. Put 0, 0 there, everything is 0 here. If x is equals to 0, then 2 multiplied by 4 will give us 8. If y is equals to 0, then 3 multiplied by 2 will give us 6. Here comes the last one. So 1.5 multiplied, that is 3 over 2 multiplied by 3 plus 2 multiplied by 1. So we are going to have 9 divided by 2 is 2. Find your LCM here. So divide here by 1 over 2 here. So we have 9, 4, which will give us 13/2. So here will be over 2. So that will give us approximately 0.5. So this is equals to, okay. So which of them will give us the maximum? The maximum will come from here. So use 4 of the y's and don't consider the x, and you will get a maximum profit of 8. This is how we solve using the graphical method. Let's look at the second method, the northwest corner method. So this is fairly easy and can be confusing as well. Big Race Tilapia is a chain of 4 tilapia restaurants. They buy their 2 kg tilapia at 3 different locations. So let's assume these are the warehouses that supply the different restaurants. Since the spot prices and transportation costs differ from location to location, the manager made a table of possible profits. So the word here is profit. Okay, so let's underline that one, profit. Each restaurant will get by purchasing tilapia from each location. The table also includes the maximum supply of each location and demand of each joint. So if we take these are the locations. So we take that as warehouses. So warehouse 1, warehouse 2, warehouse 3, they can supply us 300, 400, and 250 respectively. Now the available storage in each of the restaurants that can contain their orders is what is stated below, and that is what we call the demand. So our problem is to look at the best possible way of getting these warehouses distributing to the 4 restaurants so that we can make a maximum profit. So first, like the name suggests, northwest. So if you draw the north pole, you will see that this is our north, this is our east, south, and then this is west. So northwest would be 45 degrees right here. So northwest corner. So that is basically the top left corner of your table. That is equals to 5 in our case. So we are going to start from the 5 and work it up through to the right bottom. Okay, so if that is the case, it means that we are going to start with restaurant 1 and location warehouse 1. So location 1, that is the warehouse, have 300. They are able to deliver 300 to us. So first restaurant can take only 250. So from the first warehouse, we give 200 to the first restaurant, and that will mean that restaurant 1 will not need anything again. So we can't say that no one goes to restaurant 1 again because they are fully booked now. So I cancel these 2 down there. So that means that warehouse 2 don't go to R1, warehouse 3 do not go to R1. The next one is 7. That is the top left corner. In the top left corner, we saw that L1, that is warehouse 1, gave 200 to restaurant 1. So that means that they are left with only 100 in their warehouse. So they can only supply 100 to any given location. Restaurant 2, on the other hand, they need 200, but warehouse 1 can only provide 100. So we give all the 100 to restaurant number 2, and that will mean that warehouse 1 is out of stock. Restaurant 2, on the other hand, they had 100 already, so they are left with 150. So who is to provide this? And what do we do to the line 1? So here we can cancel this because there is nothing in warehouse 1 and they cannot give us anything anymore. So what's left is warehouse 2 and warehouse 3, and we still need some pieces of tilapia in restaurant 2, that is 150. So location number 2, that's warehouse number 2, go to destination number 2, restaurant number 2, and give them the additional 150 that they need. So we are giving them the 150 here. to fulfill everything. So to tell, and that will tell warehouse number 3, don't go to destination number 2 again, because we have already provided all they needed. However, L2 has given out 150, so let's take out the 150 from here. Then we are left with 250. So we can provide again from warehouse number 2 to restaurant 3. Let's give them how many? The 250 from warehouse 2, because they need 350, and what is left in warehouse number 2 is just 250. So give all to restaurant number 3 and empty your stock. In the restaurant number 3, they will still need 100 more. So 100 more, we can get that from warehouse number 3. So tell warehouse number 3. So in the second case, in the warehouse number 2, this we can cancel it, because there is nothing in warehouse number 2 that can provide or supply restaurant 4 again. So this one we have 100 left, and then the 250 that is in warehouse number 3, we can give 100 to restaurant number 3, leaving 150. So the 150, that is the exact requirement of restaurant number 4. So give the 150 from warehouse number 3 to restaurant number 4, and that will meet their requirements, and there will be nothing else left in warehouse number 3. This is an example of a balanced case, so you don't have anything left here. So in some cases where you have an unbalanced situation, you can have more supply and the requirements are less, so you will end up finishing the supplies and you still have to send some back to the warehouses, because you have met all the requirements but you still have some surplus left. How then do we get our profit here? So the profit is simply the product of the various distributions multiplied by the profit, the unit profit per each given point that we have allocated. So in this case, we can say our profit is equals to 5 multiplied by 200. That's the first one here. Then we add that to the product here, 7 multiplied by 100 plus, we come to the next one here, 5 times 150. Then we go to the next one, plus 4 times 250, plus, go to the next one, 8 times 100, plus, last but not the least, 5 times 150. So this is the combination that we have to do to get our profit. Now let's do the calculation and see what we're likely to get. So I'm going to use my calculator, so punch your calculator and let's be sure that we're getting the right answers together. I get 5,000. Okay, so we get a profit of 5,000 Ghana cedis. If we were to use the northwest corner method to place our orders or distribute from warehouse number 1, 2, 3 to the various restaurants, we are looking at the maximum profit, but this time we are looking at where do we have the maximum profit. So looking in the whole table here, we have 8. Okay, so the first one is 8. 8 is more than all the other values that you can see here. So we are going to go to 8 first. Warehouse number 3 is providing 8, but how many are we getting? 200. However, restaurant number 3 needs 350 and not 200. Not a problem. So let's give them the 250 from warehouse number 3, leaving 100. So that means that there is nothing left in warehouse number 3, and warehouse number 3 cannot provide anybody anymore. The next maximum is the 27 that we see. So actually they're all giving us the same thing, so there is no problem choosing from any of them. So I'm going to go with the left one. Okay, so the first one to my left. So I have L2 providing R1. So here is my next value. So I want to provide R1 200 from the 400 in warehouse number 2. So give this 200 so that R1 will be satisfied, but then we still have 200 left in warehouse number 2. So warehouse number 1 cannot provide to warehouse number, restaurant number 1 again, because they don't need any more. The next value, highest value, is 7 again. So this 7, this time L1 is providing R2, and R2 requires 250, and L1 can give more than that. So let's give all the 250 to R2 so that this will be satisfied, and we don't need to come there again. But then we still have something left here called 50. We have 50 units still left in location number 1. So next we have 6 as the biggest value. Let's take the left biggest value and give the 50 from warehouse number 1, give all to R3 so that that place will be empty. But then we still need 50 from here because they needed 100 more. We are able to provide 50, and this time we are coming to add to the 50. So in this case, warehouse number 1 cannot give again to anybody. So the next biggest value is the L number 5 here, corresponding to warehouse number 2 and restaurant number 4. So what are we giving here? We are giving 150 all to restaurant number 4. They won't need any again, but then warehouse number 2 will still have 50 in stock. That 50, give it to the last point here, which is restaurant number 3. They needed 50 and I have 50, so send it here, and that completes our table. So the same way we are going to calculate our profit by taking the product of all these points that we have provided somewhere. So we're going to have P equals to 7 multiplied by 200 from the first location here. Then the second location here we have plus 7 multiplied by 250 plus the next one here 6 multiplied by 50 plus the next one here 4 multiplied by 50 plus this one here 8 multiplied by 250 plus, last but not the least, 5 multiplied by 150. So again, we are going to punch your calculator to see what value all this will give us. So by doing this combination according to my calculator, I have 6400, so 6,400 Ghana cedis profit. So looking at this and looking at the second one, the first method that we used was 5,000 Ghana cedis. So obviously this one is giving me much more than if I had used the northwest corner. So using the maximum method, I get more profit than the northwest corner. Let's move to the next method and see how that is done. So in this method, we consider the least cost. So instead of profit, this time we are looking at transportation cost. Okay, so if I'm going to order from warehouse number 1 to restaurant number 1, how much will I pay as transportation? So in this one, we are assuming that you are the one to pay the transportation for all the orders that you are going to place. So every number that you're having right here, they are all cost, unit cost, but not profit this time. So we're looking at the minimum cost. So the minimum cost is 3, as I can see. That's the least cost item here. So who is providing the list and to where? Warehouse number 1 can provide the 250 that restaurant number 2 needs at a lower cost. So let's go there first and give them the 250. This is satisfied, but then we still have 50 more left here. The next smallest is number 4. So if I have provided all that R2 needs, then I can cross out these two because they don't need anymore. So L2, L3 don't have to go to that place again. So the next least cost is 4. That is L2 providing R3. How many are they providing? Again, they are able to provide restaurant number 3 all because they have 400, and restaurant number 3 only need 350. So let's provide the 350 here so that this will go off and this one will be left with 50 again. Now again, we have R3. They don't need anything again, so we tell L1 not to go here, tell L3 not to go here. The two are satisfied. So we are left with restaurant number 1 and restaurant number 4. So who is going to go where? Now we have 5, 5, 5, 3 of them. Choose the one that you want. All of them will give you minimum. So what I'm going to do is to come to the last one, that is L3 providing R4. So I'm going to give this all the 150 that they need so that R4 will be satisfied as well. And what is left here, it's just 100. So nobody will go to restaurant number 4 again because they have all they need. So this in the supply side, L1 still have 50 in stock, L2 still have 50 in stock, L3 still have 100 in stock. So we go back to the very first column, R1, then go to go to R1 and provide them with 50 from L1. So 50 is gone here. Come to the 6 one here, this 6 units cost, that is L3 providing R1. We give them the 100 that they need, so that is 150 already. So 150 is taken from here, that will be 50 left, and that 50 L2 can provide that 50, and they too will have nothing left in stock. So we have finished the allocation, and this is the best possible combination using the least cost method to place your orders or to distribute from the various warehouses. So let's do the calculation here and see what we get as the minimum cost to be paid as transportation for all the deliveries. So let's say cost is equals to 5 times 50 plus 9 times 50 plus 6 times 100. That's the first column. Then the second column plus 3 times 250 plus, we go to the fourth column, 4 times 350 plus, we go to the next column, 5 times 150. So the minimum cost according to my calculator is 4,150. So if you're using this method, you pay a minimum cost of 4,150 Ghana cedis. Okay, 4,150 this way.